Today's lecture is oriented to the yarn strand as a stochastic process. It is known from practical experiences from textile laboratories and so on that the mean value of yarn strand as well as yarn breaking strain and coefficient of variation of yarn strand are changed in relation to gauge length which we use on breaking machine. Why? It's a theme of our today's lecture. We will speak about the Pearce model, which is relatively old and the easiest model. In the second part of this theme, I will in short comment our model, which is much more difficult and need understand the tools from more special tools from theory of probability, especially from stochastic processes. Well, let's start the model according Pearce. You know that yarn strength is a random variable. It's evident. The probability of breakage of one section of yarn of length L at a force S, we can call under the symbol FSL. S is strength of yarn portion, yarn part, which we studied. L is a gauge length which we used, okay? So that S is a random variable. L, it is some parameter which we know. We know in which length we have our yarn, which is the gauge length by our experiment. So that FSL has a sense as a distribution function of strand S. Yeah? At the length L. And the probability of survival is 1 minus FSL. Probability of break is FSL, so that the probability that the portion is not breaked is 1 minus. Well, let's imagine some yarn length L like this here. Yeah, for yarn length L between a couple of jaws. This length L, let's imagine divided to n small lengths L0. Then evidently L is n times L0 as is shown. The probability of breakage of one section of length L0 is independent of the probability of breakage of any other section. This assumption is very important and it creates a basis of Pearce's model. We assume that the strength of short parts of the yarn, length L0, are mutually independent. Yeah? You can imagine abstractly, when you cut it, your yarn to set of short segments length L0, then you mix the segments together and then randomly you take the one beside the other and glue it together, you obtain new yarn. But you, from point of view of of strength, your result will be the same because the strengths are not mutually dependent. They are independent. Based on this assumption, the model is created. The second assumption is that the longer section must not break until any of n shorter sections breaks. This is the principle of the awake link theory. Weak's link theory started from the idea of chain. Let's imagine a long chain created from links, one link beside the other. Yeah? So, how is the strength of this long chain? This is equal as the strength of this link which have the minimum, which is weakest. Yeah? Which have minimum quality, mechanical quality, I can say. Yeah? Well, so this is the principle of the weakest link theory. Under these two assumptions, the following expression is valid. It is shown here. What's the sense of this equation? FSL is distribution function of strength on the yarn portion length L, relatively long. Imagine it as a long. What is it? 1 minus FSL. What is it? 1 minus FSL. No, it's the probability that this long length will not be destroyed, will not be braked through our force S. Is it so? Yeah. This distribution function. And what is it? Let's imagine that this long length of the yarn is not braked. It means that the strength of the first link must be higher than our force S. How is the probability of this? 1 minus FSL0. This is the distribution function of the force F, braking force F, by length of yarn L0, short length of the yarn L0, isn't it? So first link, the probability that it will not break is 1 minus FSL0. Okay? How it is with the second link? Same. The links are independent in our model now. So the probability that the second link will not be destroyed is also 1 minus FSL0. Clear? Yeah. How is the probability that both will not be destroyed? We must multiply probabilities. Yeah? And so we can go from first to the last link. How many links is there? N. Yeah? So we must multiply this quantity n times. It's from first link, from second link, third, and then to n. Okay? So that it is 1 minus FSL0 power to n. But n, it was L by L0, isn't it? So it must be, on the place of n, we can write L by L0. We can obtain this equation as well as this equation. FSL, distribution function of strength of our yarn by length, long length L. It is 1 minus, and in bracket is 1 minus FSL0, distribution function of same force S by your short fiber segments L0, power to L by L0. So now we have some reset, how from distribution of the strength from short segments to obtain the distribution of strands by long portions of the yarn. Probability density function is principally clear question now, because probability density function, it is a derivative of distribution function every time, isn't it? So we can say that the probability density function FSL, it is derivative of the function FSL by S. Yeah? It's partial because also the quantity L is here, but L is parameter, it is not a random quantity. Well, analogically for length L0, Fs L0 is the derivative of function Fs L0 by L0, by gauge length L0, by ds. So that the probability density function FSL is we make the derivative of left as well as right hand side, and we obtain FSL at this here, so that is this here, then this, but this was PDF of related for short lenses, so that the probability density function of the distribution of yarn strand using long gauge length L is given by this equation. Yeah? It's good to know because in short lengths, I don't know, for example, for 5 centimeter gauge lengths, we can in laboratory to do it. It's very difficult to say how it will be, make some prediction how will be, for example, the distribution of yarn strand using the yarn lengths, I don't know, for example, 5 meter or 3 meter or 500 meter. Yeah? Very long. So constructed instrument we have not in our laboratory. We have not breaking machine which where is possible to have gauge lengths, I don't know, 5 meter, yeah, or 500 meter. It's sometimes very important because, for example, weft lengths in modern weaving looms can be 2-3 meters without problems. No, 50 centimeter it is standard gauge length in based on standards in laboratory. So we can recalculate the probability density function or distribution function from short lenses related to short gauge lenses to the distribution on the longer. The Pearce assumed also a third assumption. He said that in a short gauge length, in our short gauge length L0, the distribution of strand, of yarn strand, is Gaussian, normal Gaussian distribution. I don't know what is more frequent in India, or Gaussian distribution or normal distribution, but I hope you know both these words. Yes. Then the probability density function FSL must be given by known expression of probability density function in a Gaussian distribution. You can say in the moment that on the right hand side we have not L0. Yes, explicitly we have not, but we have, because on the L0, the L0 determine sigma 0, standard deviation, and mean value in our short length L0. Yeah? Therefore, implicitly it is there. Okay. And the distribution function? The distribution function FSL0 is an integral of this. Yeah? It is renamed the quantity because integrating variable must be other than the border, so that using integral from our probability density function we obtain this here. You know that this integral based on normal distribution, Gaussian distribution, this is an integral have not a primitive function in an analytic form. It exists, but it is not possible to write it in an analytic form. It is so-called Gauss-Laplace integral. Under this term, you can You can find it in some mathematical handbooks, and it exists a lot of method how to numerically to obtain the best approximation of this integral. You also know that it is possible that we often work with so-called standardized Gaussian distribution, isn't it? If our random quantity S have Gaussian distribution, then the quantity S minus S bar 0, it means mean value of our yarn strength in a short fiber lenses by standard deviation, corresponding standard deviation, it is a quantity U having standardized Gaussian distribution. You know it from theory of probability, I think. And this quantity U have the probability density function is phi U, which is given by this expression, also very known from literature. And its distribution function, capital phi U, it is integral from this, so that this here. The values are usually in some statistical tables or exist some numerical method because problem with this integral, I said it. Hence, we can write FSL0 is this here or this here, where phi is a probability density function of standardized Gaussian distribution. And for F, capital FSL, distribution function, we obtain, using integral, after this such substitution, we obtain this formula. But this is a distribution function of standardized normal distribution set, which we call here as a phi. This function is very known, it's in each book. So this is a distribution function of standardized Gaussian distribution. Well, and now how it is with our distribution of yarn strength on the long lens. We derived 1 minus FSL is 1 minus FSL0 power to L by L0 using relations derived on the earlier slide. We obtained that it is 1 minus phi in the point S minus S0 bar by sigma 0 power to L by L0, or FSL is 1 minus this here. If it is right that the distribution of strength in short lenses is given according to the Gaussian distribution, then on the long gauge length L, the distribution function is given by this expression. So that we must formulate the distribution function of standardized Gaussian distribution and calculate it in the points S minus S0 bar by sigma 0. What we need to know the mean value S bar 0 and standard deviation sigma 0, which have the short lenses. Yeah. For example, when we make some experiment, and from this experiment we know that mean value on 5 centimeter. Let's imagine that the short lens is 5 centimeter. So we will use the gauge length, short gauge length 5 centimeter L0, and from a laboratory we obtain mean value of strength and standard deviation through the very, very standard method for evaluation of set of data. Yeah? So we have S0 bar and sigma 0. Yeah? And now, how is the value of distribution function in, I don't know, half meter gauge length? Yeah? Standardly we use half meter gauge length in yarn. Okay, half meter gauge length. L is 1/2 meter. How is this value, how is this distribution function? It's easy. You must calculate these functions phi, standardized Gaussian distribution function in all points, or a lot points, it's numerical, points S minus S0 bar by sigma 0. Yeah? So, is it clear how to apply it? And we obtain distribution function for long lengths. When we saw through this way, we obtain the distribution function for 1/2 meter gauge length. We can compare it with experimental results created on 1/2 meter standard gauge length. But we can through this way also obtain the distribution of strands, which probably will be right for the gauge length 5 meter, for example. And we haven't chance to experimentally obtain from laboratory. So special braking machine we have not. From this we need some big dance room for such braking machine. Okay, this distribution function. You can see also here that this distribution function on the gauge length L, another gauge length, follows this expression so that it is not Gaussian distribution. Yeah? Gaussian is in this case only the distribution on the starting short length L, length is all L0. We can also derive the distribution function, which is the derivative from probability density function, which is the derivative from distribution function, and so we obtain such using this easy way. Yes. Because better understanding, in the moment I don't know what is your value as 0 bar and sigma 0. What is your value, mean value of strand in short gauge length, and what's your standard deviation? Nevertheless, we want to have some better picture how is also graphically to explain how is the how are the relations, how is the changed this all quantities and functions. Therefore, let's introduce some linear transformation, which is here. U is S minus S0 bar by sigma 0. When on the place of S, braking forces, give the values from gauge length L0, then it is standardized random quantity. Yeah? But when on the place of S, you use random quantities from another gauge length L, then I cannot call it as a standardizing, then it is linear transformation. Yeah? For example, I have values from 1/2 meter, breaking the strands from 1/2 meter, and now I construct the quantities U, random quantities U, every time the strand from the yarn by length 1/2 meter, minus mean strand value by gauge length 5 centimeter, by standard deviation, by gauge length 5 centimeter, by L0. Yeah? That's a linear transformation. It is possible without problem to rearrange our equation to a new distribution function, no distribution function of S, braking force, then distribution function of so defined linearly transformed quantity named U. And I obtained the distribution function GUL. Yeah? It's evident based on this derivation, it's very short and very easy. That is GUL is 1 minus phi U power to 1 by L by L0. And the probability density function we obtain similarly. It's derivative from this here. It is shown here. After the derivative it is here, but it was F. This is on the place F. SL, and this is from the S, so that we obtain the probability density function in such form, or especially because Gaussian distribution, then capital Phi is a distribution function of standardized Gaussian distribution, and we obtain this equation for practical application in graph. And we can show how is the probability density function for different lenses L. If the lens L is here on the graph, the abscissa is the quantity U, the linear transformed braking force strength of the yarn. And on the ordinate is the probability PDF, probability density function GU for different gauge lenses L. If L is equal L0, so that our experiment is also on our minimum gauge length L0, then we must obtain, because it was our assumption, we must obtain Gaussian distribution. In this case, it's not standardized Gaussian distribution. This thick curve here, yeah? When we have, for example, lens 50 centimeter and starting L0 was 5 centimeter, then 50 centimeter is 10 times longer gauge length. So then L by L0, where is the curve for L by L0 is 10? It is this curve, yeah? It is this curve. Yeah? It's another distribution. It's another distribution. The position of this hat of probability curve of the probability density function is going to the left-hand side, to the small u values, yeah? And I can say thickness of this hat is a little smaller. Standard deviation is smaller, as well as coefficient of variation. You can see that we can calculate it for different values L by L0 here, and it corresponds principally good to our laboratory experiences. Means when we use longer gauge length, then the distribution have the mean value smaller and standard deviation is smaller too. By the same product, same yarn. Yes. So you can see how it is. You can also see that the curves, this is right Gaussian distribution. When we use very high value L by L0, it is also by your eyes to see that this curve is not Gaussian. For example, this curve is not fully symmetric. See it? Yeah? So it's another distribution. It's another type of distribution. Each gauge length have some other distribution. Only the lengths, gauge lengths L equal L0 have our starting Gaussian distribution. It's possible to evaluate also some statistical characteristics. U bar, which is given here, or alternatively S bar, mean values, which can we then evaluate using this expression. We can evaluate the square of standard deviations or dispersion variance of U, and using this one also the variance of S, strength values, which is here. Then, of course, standard deviation as a square root from dispersion from variance. Then we can evaluate another important statistic as, for example, coefficient of variation, V, U, as well as Vs. We can obtain also skewness using this expression here, or this one, as well as courtoisies of our curve, of our the probability density function. This graph shows different statistical quantities as a function of gauge length. Important are these two thick curves. The mean value, the mean value is this curve. It is shown that the mean value of strength with increasing of the gauge length, this ratio L by L0 is decreasing, and standard deviation is decreasing too. There is also the part for shorter lenses than L0. Partly it is possible to go also to another side, but for us it's enough to understand how it is from L0 to higher gauge lenses. Well, this all is nice, but it needs to use a relatively no to nice numerical method by calculation. Today it's principally possible, nevertheless, for people which are able to prepare some computer program, some software for such evaluation. Pearce created it around 1930. In that time, don't exist computers. And I must say that based on my meaning, Mr. Pearce was very genial and very high educated person. Because this was too complicated for to calculation this final values by hand only. He proved to construct some approximation equations. And when you studied this material, you can see how deep was his education in theory of probability and properties of probability density functions and so on. Resulting equations which we obtained as an approximation of our way, because we need for mean value this integral, we need for standard deviation or variance then this here, So it is very difficult. Integral is not analytical. I said it is Laplace-Gauss integral. So it was very difficult, but he found something which is a relatively good approximation. In my book, as well as in older books, for example, Jurek have it in his Structure of the Yarn, the Polish book, is compared how is the difference between this approximation and the original results, and I can say they are not practically too important. So that we can very well to use following equations. He said that sigma u, which is sigma s by sigma 0, sigma s is standard deviation of the strand by length L, our length, long length L. Sigma 0 is standard deviation by of yarn strand by gauge length L0. And that is ratio is L by L0 times minus 1 by 5. The second equation is that the U bar, which is S star minus S bar minus S bar 0, mean value of yarn strand on the gauge length L minus mean value of yarn strand by gauge length L0 by sigma 0, standard deviation of yarn strand on the short length L0, therefore 0, is 4.2 times L by L0 power to 1 minus 1 by 5 minus 1. We can also, this result of Mr. Pearce, rearrange the following form. Some parameter A is S0 bar minus 4.2 times sigma 0. The other parameter B is sigma 0 times L0 power to 1 by 5. And then S bar is A plus 4 by 2 B times L power to minus 1 by 5. How to practically use these equations? For example, you will study some weaving process, let's imagine, in a very modern weaving loom where weft yarn will be, I don't know, 3 meters, for example, long. Yeah? We need to have some informations. How is the distribution of the yarn strand by gauge length? The gauge length is the length on which is on which we exponent our weft yarn. Yeah. So symbolic gauge length 3 meters. It's not possible with standard breaking machine. But you can same yarn study in your laboratory, and you can study it, for example, using 1/2 meter standard gauge length. So you can think, okay, my short gauge length is 1/2 meter, L0. My long length is 3 meters. I absolve the work in laboratory, and I evaluate standardly the values of yarn strand. And what I obtain? I obtain S0 bar, mean value of yarn strand by 1/2 meter gauge length, and standard deviation, sigma 0, from our data. Yeah? So these two are known. Then I can obtain the parameter A. I can calculate the parameter A, as well as the parameter B, where on the place of L0 is now 0.5 meter, our short length. Yeah? Are you able to calculate both? And how is the mean? Mean strand by 3 meter long gauge length? You have this equation here. Yeah? And so on. So that through this way is relatively easy possible to obtain the mean value and standard deviation and so on to the gauge length which you don't measure based on the results which you measured. This graph is one of graphs from a work of Dr. Dipendas from years in which he was by a university, isn't it? The points here are experimental points. It's an example from some yarn, which of combat yarn 7.4 from cotton it is. The yellow points are experimental points. Based how we measured in our method. We used 5 centimeter gauge length as a shortest. 5 centimeter was for us the shortest L0 gauge length. Why we use 5 centimeter? Because smallest gauge length must be longer than each fiber. In other case, you don't measure strength of the yarn, then partly you measure strength of fibers. When we used, for example, 1 centimeter gauge length, then a lot of fibers you will have in both jaws. So it is not the strength of the yarn, then the from 50% strength of the fibers. Yeah? So that we chose 5 centimeter as a short gauge length. And then we measured one beside other, one portion, 5 centimeter, second of that, and so on. So we obtain a lot of 5 centimeter lenses and so on. And from this we evaluate also the strength on the different other lenses. There are experimental points from different gauge lenses. The yellow. Based on the shortest, it means 5 centimeter gauge length, we derived the parameters which are necessary, and we derived the red curves which are here. This red curve show the Pearce mean value in relation to mean values measured, experimental values, and the second graph show the standard deviation which is measured, yellow points, and the values constructed from the shortest gauge length. Therefore, in this point, 5 centimeter, it is 5 centimeter, 50 millimeter. The experimental point as well as the red curve are in same point. Well, you can see that principally this theoretical concept corresponds to the reality. Yeah? It corresponds to the reality. Nevertheless, some distances you can see the red curves are a little under our experimental points, isn't it? Yeah, it's typical for the situation. Why? I want to say in our next lecture. So, in the moment, thank you for your attention, and the next lecture we will continue with notes to the possible modification of this Pearce concept. Thank you for your attention.